Okay, welcome back to lesson 1.5. In the next part here, we're going to talk about different strategies for calculating limits. So when we calculate the limit as x approaches a of f at x, we use the following strategies. The first strategy is always direct substitution, and that's what we've been trying to do all the time. Just when can I plug in a for all the x's and calculate my answer, right? That's what I want to be able to do. When we do that, we're using a combination of limit properties that we just took a look at, and we just plug in that number. Sometimes it does not work, and you've seen that before. Sometimes the denominator is equal to 0, or sometimes we get something called the indeterminate form. So this is a phrase you're going to see throughout any calculus courses that you take, and that means when you get 0 over 0. So whenever I get one of these two things, I'm going to try one of these other strategies, and you've already worked with a few of these. So the first strategy is always simplifying or factoring. So simplify it until direct substitution works. Another strategy you've already seen is rationalizing the numerator. So you're multiplying by the conjugate, and then you simplify, and then you try to use direct substitution again. Another strategy is trigonometric identities. Here we're going to replace part of the expression with an equivalent expression. So you can think about like if I had sine x over cos x, maybe I replace that with tan x or something like that. And then we use direct substitution. It could also be like a compound angle formula or something like that. My fifth strategy, and we're gonna look at an example later in this lesson, is called change of variable. So that's when I'm dealing with kind of like a difficult root, like the cube root of x. This is hard for me algebraically to simplify away. So what I do is I replace it with a new variable. I typically use w. And then what I have to do is replace all of the other x's in terms of w as well. So the cube root of x is w, and then I'll find if there's an x somewhere else, then it's going to be w cubed. And then I can try to simplify away until direct substitution works. And then our last strategy, we typically don't use this one very often. It typically comes up when we've got a vertical asymptote, and you have seen this in lesson 1.4. This is where we separate the limit into our left and right sides to see if they arrive at the same value or not. All right, so special notes here. Rationalizing the numerator. This is typically when you've got like a sum or a difference of roots. Trig identities, you're not going to see it in this course. But in future calculus courses, that's going to come up. And I think that's it. We're going to take a look at examples with the other stuff. All right. So, example 1, evaluating each limit if it exists using an appropriate technique. In some of your homework questions, they tell you specifically which technique to use, and other questions in your homework, they ask you to choose the technique. You're most likely to see a question more like this on a test for me where I ask you to choose the technique. All right, in my first question here, the first thing I always check for is, can I use direct substitution? And if I put in x equals 2, I'm going to get 0 in the denominator, so no, I can't. My next strategy that I always check for is, can I simplify or factor? And I can. I can factor out that numerator. What I'm hoping is that it's going to cancel nicely with that denominator. All right, so you can use decomposition. I would suggest that you go off to the side to do that rough work. Here, I use kind of a guess and check method when I've got some nice coefficients. So here I've got a nice coefficient of 2. That means it's got to be 2x times x, right? That's the only way I'm going to get 2x squared out. And then when I look at the last number, it's going to come from multiplying these two constants at the end of the binomials. So I'm looking for something times something equals -2. Well, the only two choices that I have here are -1 and +2, or +1 and -2. And then I'm not sure about the order. So there's 4 possibilities for me. And I just kind of work through those in my mind until I come out to the pair that are going to add up to -3 if I FOILed it back out or expanded it back out. So what I see here is if I had a -2 here, when I multiply that with this bracket, I'm going to get -4x, and then plus 1 more x would give me back the -3. Again, if you don't like this method, use decomposition, go off to the side. If you can't remember how to do decomposition, Google it. All right, so now I've got a matching bracket on the top and the bottom, so I can cancel those. Yay! Again, don't forget at this point that we're used to just writing like this, but we have to have the brackets around this expression. Otherwise, it looks like you're only taking the limit of the first term. So now that I've gotten rid of the denominator, I can do direct substitution. I'm going to plug the 2 right in there. And I get the answer 5. All right, next question. Again, first thing I check for is direct substitution. Can I put x equals 0 into this equation? No, I can't, because then I'd be dividing by 0. So my next strategy is to try to simplify or use factoring. I'm not going to be able to use factoring here in this numerator to try and simplify this. So my next strategy, especially when I see a root with like a subtraction or an addition, is multiplying by the conjugate. So leaving that first fraction the same. Remember, multiplying by the conjugate is just creating that difference of squares. So it's still the same root, but instead of subtracting 2, I'm going to add 2. And if I multiply the top by that, in order to not change anything, I have to also multiply the denominator by that. And I'm taking that limit of the whole expression. All right, now I'm going to expand this out. Remember, I don't expand the denominator. Don't do that. You're trying to get the x to cancel away, so you want it factored out. You'd be like wasting your time because then you'd have to just refactor it out later. All right, but the top is going to multiply out nicely. It's a difference of squares, so remember those two middle terms of plus 2 times the root and minus 2 times the root are going to cancel away. So I'm just going to be left with the root times itself, so just 4 plus x, minus, and then it's going to be negative 2 times positive 2, so minus 4. And this is where the magic happens, right? If the magic doesn't happen, something's probably gone wrong. We've got 4 minus 4. All of these questions are kind of set up for you so that the magic will happen, right? So what I've got here is x in the numerator and then x times the bracket in the denominator. And then I can cancel away because I've got a multiplication. And now I check, can I use direct substitution? Can I plug x equals 0 into this expression? Yes, I can. It's not going to give me 0 in the denominator. So I've got 1 over 4 plus 0 in the root plus 2. So I get 1 plus 2, 1 over 2 plus 2, or 1 over 4. All right, part C. So for this one here, again, I start by looking for direct substitution. Can I plug x equals 8 in? No, I can't. Then I look for, can I simplify this? So can I factor it so that things will start to cancel away? No, I can't do that either. So then I look for difference of squares. Well, I'm not going to be able to write, like even if I were to square this last term, it's not going to get rid of the root for me, right? Because it's a cube root. So difference of squares or conjugates is not going to create any kind of magic for me. So this is a more difficult root. So what I'm going to do is off to the side, I'm going to create some new expressions. So I'm going to create a new variable to get rid of that root for me. I don't like the cube root of x, so I'm going to call it w. Now, what I see though is that I've got these two other places where I need to figure out, so I need an expression for x and I need an expression for like x going to 8 is the same as w going to what? I got to figure that out. Okay, so we're going to already replace this guy, the cube root of x. So what is x then? What I'm going to do to solve for x in this expression is just move the cube root over to the other side and it becomes cubing. So now I know that x is the same as w cubed. So I'm going to replace that guy there with w cubed. But I still have to figure out what is x approaching 8. What is that the same of in terms of w? Well, x approaching 8, I'm going to try and turn that into w's. So remember, in order to turn that into w, I need to turn it into the cube root of x. So if I take the cube root here of x, then I need to take the cube root here of 8. And so that's going to be approaching 2, right? The cube root of 8 is 2. And the cube root of x, that's just the same as w. So x approaching 8 is the same as w approaching 2. So that is what I'm going to replace, right? My x approaches 8 is now w approaches 2. So now I'm going to sub all this stuff into my original expression. So my original limit is now no more x's allowed, only w's. W approaches 2. Okay, so I've substituted all of that in. Now I need to try and, now I'm going to see if I can do direct substitution. So if I put w equals 2 into the denominator, I'm going to get 8 minus 2 cubed, but 2 cubed is 8. I'm going to get 8 minus 8, that's 0. So I still can't use direct substitution. So now I'm going to try to use some sort of simplifying or factoring. What I notice is this denominator is 8 minus w cubed. 8 is a perfect cube, and w is a perfect cube. So I'm going to use my difference of cubes pattern from advanced functions. So hopefully you remember that. If not, you want to Google it or grab your notes from advanced functions. When I take a difference of cubes, I'm going to end up with like a short bracket and a long bracket. At the front of the first bracket, I take the cube root of the first thing, so the cube root of 8 is 2. And then at the back of the bracket, I take the cube root of the second thing. The cube root of w cubed is just w. It's a difference of squares, so this first bracket is also going to be a difference. Now to figure out the terms in the second bracket, I use those two terms that I just figured out. So I take the 2 and I square it to come up with the first one. I take the w and I square it to come up with the last one. It was negative w squared, so it's going to be, so it's going to be positive w squared. Right, a negative square gives me a positive. Now to come up with the middle term here, I multiply these two terms together. 2 times w is 2w, and I flip the sign. So instead of being subtraction, it's going to be addition. You should only ever end up with one subtraction sign here. All right, so there's my difference of cubes pattern, and what do you know? I ended up with two matching factors, top and bottom. I can cancel those away. What? It's like magic. You can rewrite that if you want this guy in decreasing order, but because it's the middle of the question, I'm not going to be too fussy on that, right? In your final answer, if that ended up in your final answer, you would reorder it. So now I'm going to check, can I use direct substitution? And yes, I can. I can plug 2 in here and it's not going to equal 0 in the denominator. So let's do that. And so what we get here is 1 over 4 plus 4 plus 4, or 1 over 12. All right, so that's what we call change a variable, right? That was a new strategy. All right, how about this one here? The limit as x approaches 3 of 1 over x minus 3. I can't simplify this guy. He's already pretty simple. Multiplying by conjugate's not going to help me out here. There's no root to get rid of. But what I do suspect is I suspect that there's a vertical asymptote at x equals 3, right? And you know that from advanced functions. So because I have my vertical asymptote at x equals 3, I want to investigate the behavior on either sides of that asymptote. I'm going to use left and right limits. As soon as I see that vertical asymptote, that's what I'm thinking. If there's nothing else to simplify away, right? Check first if it's a whole, see if it cancels. But here there's nothing to simplify. So what I'm going to do is look at the left and the right. So we'll look at limit as x approaches 3 from the left of our function. And what happens here, so again, I'm thinking about a number just slightly smaller than 3, so like 2.99999. And if I plug that in and I subtract 3, I'm going to get a number really close to 0, but just on the negative side of 0. And when I think about taking 1 and dividing by a really, really, really small number, I'm going to get an infinity. But here I've got a positive divided by a negative, so it's a negative infinity. And then I'll investigate the limit as x approaches 3 from the positive side of 1 over x minus 3. So this time I'm thinking about a number that's just slightly bigger than 3, so like 3.000001. I plug it in here for x, subtract away 3, and what I end up with is a number that's really close to 0, but just on the positive side of 0. And again, when I take 1 and I divide by a number that's really close to 0, but not quite there, notice that I'm not doing 1 divided by 0, I'm doing 1 divided by 0 slightly to the positive side. What I get here is an infinity. And because I've got a positive divided by a positive, I'm going to be getting closer to positive infinity. And this is what we suspected, right? We were familiar with this graph, but now we've just proved it using calculus techniques. So you already knew what was going to happen, but again, we're proving calculus techniques, not advanced functions techniques. So therefore, if the left-hand limit does not equal the right-hand limit, then the limit as x approaches 3 of our function does not exist. All right, example 2. Does the limit of this big messy function as x approaches 3 exist? Use an algebraic method and then illustrate your answer by sketching a graph of the function. Okay, so this function involves some absolute value bars. So remember that the absolute value means take the answer and make it positive. So things are going to switch when I get to x equals 3, right? When I plug x equals 3 in here, this is going to equal 0. If I plug in anything a little bit bigger than 3, then I'm going to get a positive answer, and taking the absolute value of a positive answer doesn't actually do anything. When I plug in something a little bit less than 3, however, I'm going to get a negative answer, and then the absolute value bars are going to flip it to a positive. So that's going to make a difference. So let's see, we're going to summarize this. So if x is greater than 3, then x minus 3 will be positive. And taking the absolute value of x minus 3 is the same as just x minus 3, right? It doesn't actually change anything. What's more interesting is if x is less than 3. So now I want to compare these two things. If this guy is negative, is what we're saying, this guy here, when I take the absolute value of it, it's going to be positive. So in order to make these two sides the same, I need to make this, so right, like this is a double negative over here. This is negative, and this whole expression is negative. So we got a double negative. And of course, the absolute value bars say positive. So now I've got a positive equals a double negative. That checks out. All right. So another way for me to write this function then, and I'm like already regretting that I didn't just name it f of x or something like that from the very beginning, and then I wouldn't have to keep writing this thing out. So the original function I can split into a piecewise function so that I can look at the left-hand side and the right-hand side. That's what I'm going to use for my algebraic method. When I looked at this with the absolute value bars, I couldn't use my simplifying factoring method. My rationalizing method or my change of variable method are for roots, so that's not going to help me. There's no trig here for me to work with. So I'm left with that left-right side thing. And so for that, I'm going to have to use my piecewise function. So what I know then is that if x is greater than 3, then this function is actually just the same as this function, right? Because these two expressions are equal to each other. So this will be equal to this. Now, if x is less than 3, what's going to happen? Well, then in order to make this equal, what we said is you have to put a negative in front of the bracket. All right. So now I've got my piecewise function. Now I can look at the limit from the left and the limit from the right. Notice that for my piecewise function, I didn't include x equals 3, and that's because it doesn't exist for this graph, right? There'd be a hole or an asymptote or something there. I'm not familiar with this graph, but I know that the graph doesn't exist there. So coming in from the left, I'm looking at this second equation. And I'm going to try to simplify this. So this one now is something that I can algebraically try to simplify. I'm going to factor the numerator. What multiplies to -6 and adds to -1 in the middle, that's -3 and +2. And you're like, what? There's that magic happening. We've got the two factors we can cancel away. And now I've just got a -1 in front as my coefficient and x plus 2. There's no more denominator, so I can just use direct substitution. I'm going to pop the 3 in there, and I get -5 for that left side limit. Next, we're going to take a look at the right limit. So this time as x approaches 3 from the positive side of our function. So now when I'm picking my equation, I'm looking for the piece of the equation where x is greater than 3. So I'm choosing this equation. Again, I can't use direct substitution here. If I put 3 into the denominator, I'm going to get 0, but I can simplify the numerator by factoring. And there's the magic. We cancel our common factors. Don't forget the brackets even after you cancel. And now I can plug the 3 in. So direct substitution, and I get 5. And you're like, well, that looks almost the same, but not quite. So here I'm approaching a y value of -5, and here I'm approaching a y value of +5. So therefore, my left-hand limit does not equal my right-hand limit. And that means then that the limit of that function, which again, I wish I had named so I didn't have to write it all out again, does not exist. They did ask us to show a picture of the graph here, which you might need to do a bit more work in order to figure out. Oh, but basically what's happening at 3 is I've got this open circle at 5 and another open circle at -5. Remember, there's actually no real value when x is equal to 3. And on this side here, what would happen is I would have this line heading up, and then over here I'd have this line heading down. All right, and that's it for today's lesson. Enjoy the homework. You can find it on the homework log.